So guys, welcome back. This is gonna be problem two or the second problem for chapter 25 review for my midterm. So we are given a cylindrical copper cable of length 1.9 kilometers. 1.9 kilometers is connected across a 220 volt potential difference pool. So that's gonna be our believe our source. The resistivity of copper is 1.72. Cool. Okay. So what should the diameter of the cable be so that it produces a heat at a rate of 60 watts? Cool. Okay. So we have, let's go ahead and just draw this real quick. Let me use this. So we are given a cylindrical copper cable with a length of 1.9 kilometers. So we'll just say that this is basically 1.9 km. So and then we convert this to meters, so it's gonna be 1.9 meters to make it easier. And then across the 220, so across would have to be, and then we'll say that the big battery is over here. Potential difference, so this is 220 volts. Cool. And then the resistivity of copper, so we have rho is equal to 1.72 times 10 to the negative 8 ohm meter. What should the diameter of the cable be? So we are looking for the diameter of cable, which is just 2 times r of the cable, and we can get r from the area, where area is equal to pi r squared. So that's eventually what we're going to solve for. It's the square roots of this, where r is going to be, well, whatever. We'll do this later. But basically, this is the r that we're solving for. And how do we get there? We can use the current density, J, which is related to R. So we have and it's also related to the resistivity. So we can actually just go ahead and write down. Oh, and we also have it produces a heat at a rate of 60 watts. Okay, so we also have power here then. Power equals 60 watts. Cool. Okay, so we can actually just write our resistor is equal to, it is L, which is the length of the wire divided by the A, times the resistivity of the wire. So this is how we find R. And then for power, we have P is equal to I delta V, where V is just the potential difference. So if we find I from delta V, we can find R, and then we can find A. So we can just go ahead and just do Ohm's law, which is V equals IR. Cool. And we can actually solve for I here. I is equal to P over delta V, because our delta V is given. This is our delta V, which is the potential difference. And then we can find the currents. And then from the currents, we can find the resistor. R is equal to V over I. I'm pretty sure, right? Yes, I'm pretty sure. And then we can, oops. Actually, we already have something for R. So, I think we could just rewrite this. So this is eventually what we want. And me doing I is equal to R delta V is going to be the same thing. So we just go ahead and just plug in. So we have our I, but we don't have R. Actually, we do have R because it's this. So we can just say that V is equal to I times L over A row, where V is just a potential difference. So that's also a given. Cool. So we have everything we need. Now we're just gonna do the math. Okay. So first we have power, so we can find the currents flowing through the wire. So we can say that I is going to be equal. I'm gonna do this in a different color because blue is for the unknowns. We're gonna go ahead and just do I is equal to the power, which is 60 watts, divided by the potential difference, which is 220 volts. This should give us amps, so it's gonna be 6 over 22, which I can't do in my head. So it's 0.273 amps. So that's our current. And if we can go ahead and just plug this into here. So we can go ahead and just plug our currents into this, and if we could solve for the R when we rewrite the area as pi r squared. Very simple. So we have our V. Our V actually here is going to be our delta V or VAB. So we can just write delta V is equals to our currents, which is given, um, multiplied by the rho, multiplied by the L, and then this is where we get our R. So it's going to be pi r squared. We can rewrite this in terms of R as well. So we can just go ahead and just multiply the R over here, divide by delta V, and then we can just go ahead and just solve for it. So we have R is equal to the square root of, these three stay the same, all over pi delta V. Cool. Okay. Now let's go ahead and just plug in numbers here. So I'm actually going to put this to the side. So we can plug in numbers over here. Cool. So we have R is equal to square root of, we have our I, which is 0.273 amps, multiplied by our rho, which is 1.72 times 10 to the negative 8 ohm meters, which is what we want, ohm meters. And then we have our length, which is right here. So this gives us meters squared. Square root of meter squared would be just meters. So it's a good sign. It's a good sign. So we have 1.9 times 10 to the 3 meters all over we have pi, and then we would have our delta V, which is 220 volts. Cool. So we have, if I is equal to, so we have amps here, which is equal to volts over ohms. So let's make sure that our units are correct. Our amps, this basically turns into volts over ohms. So that cancels, that cancels. This gives meters squared, and meters squared, the square root of meters squared is just meters. Okay, so we are actually correct here. Cool. Let's plug this into our calculator. 0.27, 1.72. Then we have 1 all over pi 220. Well, so we're given a really small number. Interesting. And I think this is okay. We should be getting a really small number. I think. Yeah, because we're looking at a a wire, a copper wire. So yeah, okay, that makes sense that we have a really small number. So the number that I'm getting is, I'm gonna erase all of this clutter. So my R is equals, I dropped my calculator. So 1.14 times 10 to the negative 4 meters. Now, we just multiply this by 2. 2R equals D. So where D is equal to 2 times this. So times 2, I believe it's just going to be 2.28 times 10 to the negative meters. Basically, 2.28 times 10 to the negative 4 meters. And that's the diameter of the copper wire. Cool.